All right, we did minimization. We got into Karnaugh maps. We are still in the middle of Karnaugh map. We did the definitions and the two variable maps. We defined adjacency, and we said the whole thing about Karnaugh maps is adjacency. Okay, and correspondence of physical adjacency and Boolean adjacency. Let's do something else, and that is going up one level or one variable instead of two variables. Let's do three variables. But the thing is, two variables, we are very limited in showing you what is what, in showing you the capabilities of Karnaugh maps, in showing you that we can do the essentials, what are essentials, prime implicates, and all that. They're very limited. So let's go up one and then talk about three variable maps. And then in three variable maps, maybe my definition of adjacency will change or modified, not necessarily changed for completely changed, but modified or revised. And also, let's see how we form our tables. This is a three variable table. So we are starting on three variables, and then we go to 4, we go to 5, we go to 6, whatever. This is a three variable table. Three variable means A, B, and C. 0, 0, 0. Here. 0, 0, 0. 0, 0, 1, 0, 1, 0, 0, 1, 1. 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Right? 8 of them. So I have to have 8 location for my three variables, 8 combination of my three variables. So I put 2 of them on the columns and then 1 on the rows. So A, B, C. So I start numbering them like 0, 0, 0, 0, 0, 1 here, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1. And then I'm used to doing after 0, 1, which is number 1. Then I am used to doing 2. So I do 1, 1, 1, 0, 0, and then 1, 0, 1, 1, 1, 0, 1, 1, 1. Okay? So I number them like this. And then let's start playing with it and let's minimize and all that. But wait a minute. Does this satisfy adjacency? Is the adjacency that is in Boolean algebra the same as physical adjacency here? Let's do this. Let's look at these two ones. Okay? Independent. This and this. And don't look at the right hand side. Look at the left hand side only here. Only look here. These two appear adjacent because they're along the same row. Okay, good. So they must be Boolean adjacent as well. So let's map them. But then wait a minute. Let's write the product term corresponding to the one on the left. It is A bar, B, C bar. That means it's A is 0, its B is 1, its C is 0. So it's A bar, B, C bar. How about the one on the right? Is A is 1, B is 0, C is 0. So it's A, B bar, C bar. Okay. They are physically adjacent, all right. Are they Boolean adjacent? No, they're not. They are not because they are true. They have the same variables, but they're different in two variables. One is A, which is A bar here, A here. And the other one is B, which is B and B bar here. And therefore, even though they appear as them being adjacent, they're not adjacent. So where did I go wrong? I went wrong in numbering the columns of my Karnaugh map. The way I numbered it was like this, the way I like to number things, okay? Start with 0, 0, 0, 0, 1, 2, 3, 4, 5, 6, 7, I'll go like this, okay? But then that's not going to work. That doesn't give me the proper adjacency. This is not a Karnaugh map. So instead of going column-wise, 0, 0, 0, 1, 1, 0, 1, 1, I go 0, 0. Now look at the right hand side. 0, 0, 0, 1, 1, 1, 0, 1, 0. Numbering becomes 0, 1, 2, 3. Okay, skip the third column, then come back to it. 0, 1, 2, 3, 4, 5, 6, 7. 0, 1, 2, 3, 4, 5, 6, 7. So the truth table is still the same, but the Karnaugh map, the third column and the fourth column are swapped. This way, let's look at the same two ones that we were looking at this year. Now let's look at the right-hand side Karnaugh map. The right-hand side Karnaugh map shows me two adjacent ones, two physically adjacent ones. The one on the left corresponds to A bar, B, C bar, because A is 0, B is 1, C is 0. The one on the right corresponds to A1, B1, C 0. Okay, because A is 1, B is 1, C is 0. And then look at these two terms. They are the same in B, C bar. There is only one variable different, and therefore the physical adjacency here and Boolean adjacency here, they do correspond. And that's the key thing. And therefore, from this point on, when I'm numbering my columns of Karnaugh map, I will go 0, 0, 0, 1, 1, 0, 1, 1, 1, 0. How about rows? Well, I can do the same thing here. If this is a three variable map, you like to write it like this, you go 0, 0, 0, 1, again 1, 1, 1, 0. Let's number them. 0, 1, 2, 3, 4, 5, 6, 7. Okay? With this in mind, let's do some minimization using three variable maps. In a lot of cases, I'm not going to show you the truth table anymore because it's just lengthy. But then you understand how to go from truth table to Karnaugh map, right? Just if you have ones in the column, just take the row numbers and then put ones in the same box numbers that correspond to those rows. But I didn't say that I will never show you. I said that once we get this started, we are not going to show you anymore. Look at this thing over here. I have a truth table on the left-hand side. Okay? And the sum of the min terms is 3, 4, 6, and 7. And therefore, this is sum of the min terms. Okay? This truth table has my function in its broken form. Okay? That means there are 4 ones. You cannot split ones into anything smaller. The smallest little elements of this function are these 4 min terms. And I'm representing this function using its 4 min terms. And then I'm going to represent the same exact function in Karnaugh map, again using its 4 min terms. And therefore, all I'm doing is turning this table into the Karnaugh map. It has let's do the numbering. 0, 1, 2, 3, 4, 5, 6, 7. 3 is 1, so put a 1 here. 4 is 1, so put a 1 here. 6 is 1, so put a 1 here. 7 is 1, oops, went a little too far. 7 is 1, so put a 1 here. Okay? So it's easy to go from Karnaugh map, from truth table to Karnaugh map, and I did. Now let's take adjacent ones and map them together. I find 2 adjacent ones, one here, and then another adjacent one, another 2 adjacent ones up there. I also find that a third pair of adjacent ones. They are adjacent, right? See, let me go back here. This is adjacent, and these 2 are adjacent as well. these two are adjacent as well. These are the prime implicants of the function. So my prime implicants are BC, BC, AB. AB is the vertical one. Okay. BC is this one. AC bar is this one. Are they prime implicants? Yes, they are. None cover the other one completely. True, the one in the middle is covered by both. One of the mean terms of the vertical one is covered by one prime implicant. The other is covered by another prime implicant, but there is no prime implicant that completely covers all of the mean terms of the vertical ones, and therefore the vertical one is also prime implicant. Okay, now let's look for essential prime implicants. This is an essential prime implicant. Why? Because the one I just put an asterisk on is not covered by any other prime implicant. How about this one? This is also covered by only one prime implicant. Is the vertical one essential? No, because you already see that there are two lines going through all the mean terms of it. A blue one and the red one for the top, a blue one and the red one for the bottom. And therefore, those are not covered by only one mean term, and therefore the vertical one does not qualify for essential. Then my minimization method says this. Start with essentials. List all the essentials. Okay? List all the essentials. The essentials are, one of them is BC. The other one is AC bar. Then it says, check mark all those mean terms that are covered. Check mark, check mark, check mark, check mark. Then look to see if there are any other mean terms that are not covered. If they're all covered, that's it. If they're not covered, then look for more prime implicants. How about the red one? The red one is a prime implicant, but for now is a useless one. And therefore, the term AB, which corresponds to that vertical one, is not needed. Okay? Let's do another Karnaugh map. Again, I'm starting with the truth table. Little by little, I'll start dropping the truth tables. 0, 1, 2, 3, 4, 5, 6, 7. I have ones in location 1, 3, 4, 6, 7. Okay, look. 1, 3, 4, 6, 7. I have ones there, and therefore what I have on the right is a Karnaugh map that corresponds to the one on the to the truth table on the left. Let's look for prime implicants. Okay. Oh, by the way, if you want implicants, fine. You have this is implicant, 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 implicant. Okay. And then prime implicant, prime implicant, prime implicant, prime implicant, which is also implicant. I don't want that. I will start with prime implicants. Okay. These two mean terms form a prime implicant. I can do two mean terms, two mean terms, two mean terms. Therefore, if you see three mean terms, that doesn't mean that you can map them because we are doing binary, so we can do only two mean terms at a time. That's one mean term. Sorry, that's one prime implicant. That's another prime implicant. That is another prime implicant. Okay. Change the color. Sometimes get confusing what colors I've used. This is another prime implicant. Okay. This is another prime implicant. Do I have any more prime implicants? Do I have any more prime implicants? No. Okay. Let's start identifying the essential prime implicants. The red one is essential because of this one here. Notice, take the ones, take the mean terms that you only see one line crossing it. Okay? And that one, wherever it is, that prime implicant is essential. Okay? Do you see any other ones that only one line crosses it? Yes, the one on the upper right hand side, there is only one line crossing that, and therefore that qualifies that prime implicant for it being essential. Let's write as the implementation of my function w equal, let's write the red one. The red one is a bar c, which is this. And then let's write this one, ORed with a C bar. Okay? Do I have any more essentials? No, I don't. Okay? Do I have any more essentials? I do not. Have I covered all the mean terms? Let's see. The red one covers this and this. These two mean terms. And this one covers this and this. Do I have any mean term that is not covered? Yes, I do. This mean term is not covered by any of these essentials. What it means is that my function is incomplete until all mean terms are covered. All right, I look at the mean term. I see a green map going through it. I see a blue map going through it. And then if I take the green, it covers one uncovered mean term. If I take the blue one, I cover one uncovered mean term. So choosing these prime implicants doesn't matter which one you pick, because both of them are covering one remaining uncovered mean term, and therefore I can write my function as either what I say, either a C bar ORed with AC ORed with AB. That's one way of writing it. Another way of writing it would be ORed with BC. Either one is fine. Look, the number of terms in either implementation is the same. The number of variables in all the alternative terms, the green and blue, are the same, and therefore this implementation has two good solutions, two minimal solutions. This implementation has is not unique. Is not unique because I had to go to the situation of selecting prime implicants. This one is unique because by choosing this essential prime implicants, you are done. You don't have to go any further. This one, you had a choice of taking the blue or the green, and therefore this is not unique. So this is what I'm showing with the mapping here, and this is the green that is selected, and this is the blue that is selected, and therefore I have two alternative solutions for my function. All right, Let's look at the implementation of the two alternatives of this function. Let's take the upper one, AB, and this is the circuit for implementing it. I have AB, AC bar, A bar C all together, and therefore this is this. Okay? Something I'm showing here is Karnaugh Map only gives me a two-level network. This is one level, this is one level. And or and, these are two levels. A Karnaugh Map can never give me three levels. Meaning and or and. The Karnaugh Map only gives you two-level minimization. And Karnaugh Map, if you want to go beyond that, then you're back to Boolean algebra, and you have to use Boolean algebra laws to, if you want to reduce it or if you want to reshape it, if you want to do whatever, after two levels, then you're with the Boolean algebra again. I'm taking this function and I am factoring let's see what I'm factoring here, A from the first one and the third one. So this becomes A, B or C bar, or with A, C bar. Why would I want to do that? Maybe there is a good reason. But anyway, this is not a two-level network, and you have to do Boolean algebra. And then I have A, B or C bar, which is this gate, A, B or C bar. This is B or C bar. And then you have the AC bar, which is this one, and then all together. These two circuits are exactly the same, except that I have done further manipulation using Boolean algebra, something that Karnaugh Map wouldn't give me. I have another implementation here. Let's do A, C bar, or A bar, C, or B, C. So A, C bar is there, A bar, C is there, and then I have B, C, and therefore what I need is a wire from here to here. Okay? So what you're seeing is that wire, that AND gate input, whether it's connected to A or it's connected to C, doesn't matter. Okay? So you can take this wire from there, put it down there, the circuit works exactly the same way. Okay, let's look at something else. These two are adjacent, right? So are these two. Let's write these two. This is AC bar. This is A bar C. What do I see? Well, this and this A C bar, sorry. This and this have the same number of variables. They are different in only one variable, and that variable is A. According to definition, this is adjacent. And therefore, according to Boolean algebra, I can combine these two into C bar, which becomes C bar, A bar, or A, which becomes C bar. Why didn't Karnaugh Map? Isn't Karnaugh Map supposed to give me all the adjacencies? So how come the Karnaugh Map didn't show me two adjacencies? Well, that's because I didn't look. The Karnaugh Map is really telling me this. The Karnaugh Map is telling me this is an implicant. The blue one is an implicant. The one on the left is also an implicant. Then it says these implicants are covered by a higher level implicant. And therefore, it's telling me the red one considers those two blue implicants. See, the blue implicants are adjacent. When I say these two are adjacent, when I say these two are adjacent, because they are horizontally next to each other. Okay? But then when I say that these two are horizontally next to each other, these two are horizontally next to each other, but then look, the two implicants are also, they are bigger implicants, they contain two mean terms, but they also are horizontally next to each other. And therefore, they can be combined into an upper level implicant, which becomes a prime implicant because nobody else covers it. So the red one is an implicant, also a prime implicant. The two blue ones are only implicants. What is this? Well, this contains variables C, A, and B, but then A and B are different in all these four ones. The only variable that is the same in all these four ones is C, and therefore, yes, indeed, without having to write any algebra, any Boolean algebra, I could map all of these four together and then come up with the C bar. Okay, which is this. Let's look at another situation here. An implicant, an implicant, an implicant, an implicant, an implicant, an implicant. Are any of these prime implicant? I don't know. But then I look further and I find out that no, they are not. Because the red and the blue are two implicants adjacent to each other, the big ones. The big red and the big blue are two implicants that are next to each other, that are horizontally next to each other. They are not across, they are just horizontally next to each other. And therefore, the whole thing, the whole big thing is also an implicant. Does anyone cover this big implicant that I just showed you? No, nobody else covers it at all. And therefore, I have this big one is a prime implicant. What's the corresponding Boolean term for it? Look, it has A, it has B, it has C, but then the only variable that is the same in all these four is A, and A is 0, and therefore W is A bar, and that's all there is to it. W is A bar. I could look at this in a different way, though. See? I could look at it this way. Same map. Okay? I could do this. This is an implicant, this is an implicant, that's an implicant. This is an implicant, this is an implicant, this is an implicant. Now I have two implicants along the same column. Again, they're adjacent. And therefore, I can map them together. So no matter how you map them together, whether you want to map them using the left map or this, it's the same thing. What variable is the same in all of these? A, and A is 0, and therefore, whether you look at it the left way or the right way, you both come up with W bar. W is A bar. All right. See, we are revising the way we regard adjacency. Not really revising, expanding it. All right. Let's do that again. This implicant, this implicant, this implicant, this implicant, this implicant, this implicant. This is a, let me do a different color. This is a prime implicant. This is a prime implicant. Okay. This is a prime implicant, maybe. This is a prime implicant, maybe, maybe not. But then what happens is, look at the two on the side and the two on the left, on the right and on the left. Okay? The two on the left are A bar, B bar. The two on the right are A, B bar. These are also adjacent. These are also adjacent, and I can write them as what? Drop A, this becomes B bar. So why did I see this in the Karnaugh map? I could see this in the Karnaugh map if I was a little bit smarter. Okay? If I look at the Karnaugh map as it, not a flat table, but a circular table, like a paper folded on the two sides. Look at the Karnaugh map as a circular map. And therefore, the two sides are also connected, like this paper is. And therefore, if you look at it this way, then you see, oh, of course, the this and this are adjacent. And therefore, the way you map it is exactly what I'm showing here. You map this, and you map this, and now let's look for shared variable in all these four. And the shared variable in all these four is not C, because C is 0 in two of them, in one in the other two. Not A, because A on the two on the left is 0, on the two on the right is 1. But B is shared, is the same in all of them, and is 0. And therefore, this becomes B bar. Okay? So you don't really have to write Karnaugh map. Boolean algebra. Finishing this, when I do all these four, actually all these four B bar is essential because, yes, it is essential because of this one and this one. Because these are prime implicants, and no other larger prime implicant completely covers it. So that's essential. So is the blue one. The blue one on the upper left is essential because of this one, because this one is only covered by that, and therefore this is A C bar, and this is essential. The one on the lower left, this one is A bar C. Oh no, this is A C bar. This one is A C bar. This is this. And then this one, because of this one, is essential, and therefore this is this. Okay? Now, with these three terms, have I covered all the min terms? Let's look. Okay? Let's look. This is covered, this is covered, this is covered, this is covered by B bar. This is covered, this is again covered. This is covered, and this is again covered, and these are all essentials, and therefore this is a unique solution to this problem. That's it. So you're mapping these on the side. So if you look at the back of this folded paper or circular paper, you see that these two are sitting next to each other, adjacent. All in all, what you have to do is you want to make sure that you cover all the mean terms. You want to make sure that you have fewer maps, and you want to make sure that you have larger maps. Okay? And you want to make sure you take advantage of the essentials, and when it gets to the point where you want to do prime implicants, you want to make sure that prime implicants that you're selecting covers the most number of uncovered mean terms. Okay? When we do 4 variable maps, we see more choices. All right, that's good for now, and then we do 4 later.